Hi, welcome all of you very warmly to our AdFiS Hackathon launch webinar. We call it Carbon Hack, Activating Sustainability via Innovation, as you can see. My name is Gudrun Mernitz. I work for Viteno, a science and technology park in the very northeastern part of Germany. And we, as Viteno, are project partners of the BioBoosters project, and we are the organizer of the AdFiS Hackathon, of course, together and in close cooperation with AdFiS and all the other BioBoosters project partners. The agenda for today looks like this. I will not read through each and every presentation, but just to let you know, there are three main parts. In the beginning, you will hear kind of overview of some of the actual application areas of activated carbon, of the potential and limitations of residual biomass for the production of activated carbon, and of course, and there will be a second part, and that's a central one, to hear about the challenge of AdFiS. But the challenge we want to launch today, and you will hear in much more detail what the challenge is about. And the third part will be the introduction, a short one, to the BioBoosters project as such, to give you the frame of everything we are doing here in BioBoosters. First achievements, I'm not entirely sure, but what Anna, our lead partner of BioBoosters, will tell you today, but I guess it will be also a kind of impact we could reach already. So we will start directly with a presentation from Thomas Wittgens. Thomas is from the University of Aachen, and he will tell us about activated carbon processes for wastewater treatment. Thomas is director of the chair of Urban Water Management and Water Quality Management and Institute of Urban Water Management. Sorry, I need to read that. As Thomas needs to leave more or less directly after his presentation, I would ask you to put your questions, if you have some, directly into the chat, that we might clarify those questions directly with him after his presentation. Okay, so Thomas, the floor is yours. I will stop my presentation, and now you should be able to share your ones.
Yes, very good afternoon. Thank you very much for the invitation. I hope that you can see my slides.
We can see them. They are not in the presenter mode so far.
Okay, then I have to check once more. Now?
Yes, now it's perfectly fine.
Okay, thank you very much. So thank you very much for the invitation. I'm Thomas Wittgens. As had been said before, I'm chairing the Institute for Environmental Engineering here at RWTH Aachen University. In German, we are called the Institut für Siedlungswasserwirtschaft, and my short presentation includes two parts, one giving an overview on activated carbon processes in wastewater treatment and our motivation to do so, and the second part will be related to the BMWF-funded RIAS project, which we have completed last year, which was on activated carbon from screening materials obtained in the wastewater treatment process itself. So first, a little bit on the motivation. As most of you have heard, the Urban Wastewater Treatment Directive, the European directive, has been revised last year. And now we have a goal, I would say a longer term goal, to equip at least the larger wastewater treatment plants with treatment stages for micropollutant removal. This is called quaternary treatment, and this quaternary treatment will go on stepwise until 2045, when all installations in Europe should be equipped. I think this is a big challenge. Within Germany and also within Switzerland, already a lot of experiences have been gained. I will talk about that later. But now this directive will make it a requirement for many, particularly the larger plants in Europe, and also treatment goals identified in the new directive, stating, for example, in Article 8, the necessity for this treatment. In Table 3, we have a reference to so-called indicator compounds, and they should be removed by 80%. There are a lot more details to that. I will talk about some later on, but let's have a look at the processes. Starting with experiences, particularly in the federal state of Baden-Württemberg and the southwest of Germany, first treatment schemes have been established. For example, using activated carbon typically coming from fossil sources, but also from coconut shells in Southeast Asia. And those materials have been used in processes adding on a conventional mechanical biological treatment process and wastewater treatment. And the first process established, the so-called Ulm process, referencing the city of Ulm, which has adopted that process, is a process with powdered activated carbon dosage in the effluent from the secondary clarifier. You also have coagulant and flocculant dosages. You have basically a two-stage separation and recycling of the carbon by a clarifier and also by a final polishing filter. There have been many, let's say, further developments based on this process. I will talk about that. But the main alternative to the activated carbon process, I also have to mention that as a quaternary treatment, is the ozonation process. So the introduction of a highly reactive ozone gas also in the effluent of the secondary clarifier to react and oxidize micropollutants, and then a filter which should be biologically active also to degrade biodegradable transformation products. So these are the two kind of benchmark processes, but there have been many other processes using activated carbon, not only in a powdered form, but also in a granular form as a deep bed filter, possibly with another conventional filter media up front to remove solids. But also combinations are on the way of ozonation and GAC filters, with the advantage that you can work in really low ozone doses and have very long run times of the GAC filter bed. So these are the main processes. What we see coming right now is a, let's say, intensified process, not using the classical mechanical biological treatment with clarifiers, but using a membrane, a submerged ultrafiltration membrane as a separation stage, and then simultaneously dosing powdered activated carbon into that membrane bioreactor. We see quite some systems on the way in that direction, but we also have really a portfolio of processes using, for example, powdered activated carbon directly in front of a deep bed filter, or also simultaneously dosing into a conventional biology. So there's a whole array of processes there. You will hear also about the two main activated carbon products, I think powdered and granular activated carbon. When we now look what is already implemented in Germany, you see, particularly in the federal state of Baden-Württemberg, you see many processes using powder activated carbon and granular activated carbon. We see also the first combinations coming on. And in the federal state of North Rhine-Westphalia, where I am based, I'm here in the very west, and Aachen has a big ozonation treatment system. Nevertheless, we see more on the eastern part of our federal state also a lot of the activated carbon-based processes, and many big systems are still deciding. So this is going on, and behind this background, we started to work on an alternative route to produce activated carbon, because it is common sense that the fossil-based activated carbon carries a big footprint and ecological footprint in different respects, and we have to look what kind of alternative options we have. And based on preliminary experiments, we adopted the approach to use screenings, to use fine screens and try to utilize the screenings a product basically derived in the wastewater treatment process itself by different routes, thermochemical routes, to produce activated carbon, which can then be used in the wastewater treatment process again. And this kind of objectives we followed up in the so-called RIAS project, and it ran between 2019 and 2024. Peter Schleifer on our side was the main person conducting it with in collaboration with many project partners, particularly the University of Hohenheim, experts in the thermochemical process, GLAD company, Huber company, HD Cycle, which provided facilities for the hydrothermal conversion process, Ruhrverband as a big wastewater utility, and KIT for the pyrolysis part. This was funded by the German Federal Ministry for Innovation and Research. Looking a little bit more in detail about the production route. So we embarked on an approach using this fine screen, some hundreds of micrometers, mesh sizes, to take out particularly the cellulosic fraction coming in of the solid matter from the wastewater treatment plant in the order of 150 to 400 milligrams dry matter per liter. And then we had different routes after dewatering and drying. We had one route using this hydrothermal carbonization route, and another direct route with pyrolysis, always having an activation step, having also a configuration step with a pelletizing activation, and then our application form was on the powdered form, so it needed some sort of grinding, and then a test-wise application in a pilot facility for biological wastewater treatment. One of the core questions which we looked at in the first phase of the project: can we achieve approximately an amount of activated carbon needed by using this route? And was quite clear from quite early on, and you will hear more about this, I think, from Corbinian. We have significant mass losses along such a process. You are carbonizing, you are concentrating, you are losing a lot of material to gain an active material, which really can act as an activated carbon. So while accounting for all these losses, in the end, we found that we can end up roughly in a range of concentrations, let's say around 50 milligrams per liter. And what we also found is that you need more of this alternative activated carbon compared to the really highly active benchmark processes, which are on the market, But we can roughly close the balance in the sense that we think that a roughly autonomous process can be introduced. We will need possibly some additional conditioner also to have our stable aggregates depending on the application. We started with a recovery of the cellulosic fraction at the wastewater treatment plant Iserlohn, Lettmate, run by the Ruhrverband. Huber delivered this wonderful pilot installation with screens, with subsequent filters, and also with machinery for dewatering. You have some impressions here from the different stages of the project. This is the screening. This is a rainy day out at the plant where we ran this fine screen. Here you see the material already dewatered. You can guess that there's a lot of cellulosic material in here, basically coming from toilet paper. And then you see the HTC plant. You see an oven for activation, where activation has been done. You see pellets, and then a glimpse of the pilot installation where actually the tests were then finally performed. In the first phase, where we ran through this process in rather small scale, we produced some carbon which we tested in the lab, and we used this specific absorption coefficient at 254 nanometers as a surrogate, as an indicator for micropollutant removal. We knew around roughly 30% of SAC reduction. We have acceptable performance, and then compared to the highly active benchmarks, we found that in a range of materials obtained from different plants and processed in different routes, without going into detail, somewhere between 35 and 50 milligrams per liter we could produce carbons which are active and perform in this respect. It was a bit more difficult, and we have to acknowledge in the larger scale, we have processed really tons and tons, about 15 tons of material to produce about 100 kilograms or 150 kilograms of the material for testing. So you see, it's a very intensive process. But also here, compared to the benchmark, when you look at the specific concentrations, they go very high here, but the lower part of the graph is interesting. For the best carbons, you can also come for an indicator list, which summarizes the main indicators according to this new EU directive. You can come to this removal rates also, let's say, still with high, but with probably acceptable amounts of the carbon to be produced and to be applied. We have found differences, significant differences between the different routes, but I think now is not the time to go into that much detail. You can certainly come back with questions to Peter Schleifer or to myself or to the project partners to learn more about our results. Peter is currently finalizing his PhD. When this is out, the full documentation will be out, hopefully, but I hope this was interesting for you as a first glimpse on our approach. Thank you very much indeed. Happy to take your questions.
Thank you so much. Very interesting, and I'm really looking forward if there are any possibilities to connect those the challenge that is in the core of this webinar, and not also in our work with AdFiS and your work. So it will be very interesting to have a look at this.
It would be nice to keep in touch on this for sure. We have completed this project, but we are certainly looking for options to also continue in that direction. And we are very interested to see what your results will be. And we wish you the best of luck with your project.
Thank you. So
Of course, there is energy needed for the HDC process. I mean, also any type of carbonization process requires energy. The economies cannot be fully assessed on this pilot scale. It will also be a challenge in terms of total cost. I think at the moment, it's really a matter, do we want to have dependency on the fossil sources, or do we want to even tap into resources which are coming from the wastewater itself? This is the prime.
Okay. So energy is also an issue within your work and will be also in the AdFiS Hackathon. So it's interesting, of course. So energy is also an issue, but as I said, so might be interesting to see any cooperation opportunities. Okay. So at the moment, I don't see any further question. Of course, you can also
for your attention and.
Thank you so much for your time. And
unfortunately, I have to go to an exam, but I will be here for a few minutes.
Okay. So, if you are still here, so for the others, if you have still a question, please put it in the chat and Thomas can have a look at this. Otherwise, let's keep in touch. Thank you so much. Okay. So our next speaker is from AdFiS, from our challenge provider already. So it's Thomas Stift, and Thomas will talk about activated carbon. We'll go a bit back to the overall picture of activated carbon, and his talk is about products, applications, and production processes to give all of you, a good overview of what is activated carbon about. Okay, so Thomas, the floor is yours.
Yes. Of course.
Yeah, we can see it. It's also not in the presenter mode.
Yeah, please.
But you
wait a minute. I will do. Now I hope it is in the right thing.
Now we can see your always the next slide. Doesn't matter, but it's also not the presenter mode.
Then I will start again. Now it is right.
Now it's perfect. You can start.
Yeah, thank you for the challenge. And I'm Thomas. I'm the CEO of the AdFiS. I'm a mechanical engineer. I'm studied some years ago at the Technical University in Dresden. Then I work 15 years in the automotive industry, and now the last 17 years at AdFiS in the activated carbon industry. The wastewater treatment is one of the topics we have heard, and I will speak something about the basics of the activated carbon, about applications, and short about different production processes. First, something about the history, I will say, that's for me important. That's why the first science about activated carbon are based around our area, around the Baltic area. And it was Carl Wilhelm Scheele. He was born in Stralsund, worked in Göteborg, Malmö, and Uppsala, and he makes studies of oxygen, nitrogen, and the absorption on charcoal in the 1770. And this was the science basic of the activated carbon, the science basic of pyrolysis and activated carbon. And so I will say the region around the Baltic area is the region of the activated carbon now. But now, between the two world wars of the last century, there was the most of research into the activated carbon. And today we produced with this results of this research 100 years ago. That's a lot of time was spent. Now is a situation that the Asian, special the Chinese manufacturer dominates the market. We have only 5 or 6 producers in whole Europe, and I think we have no so much research, we have no so much teaching. I'm happy that we today have 2 speakers from universities, but it's not the must. And I think we need for water treatment, for air purification, for industrial applications, a lot of carbon, and we produce not enough. All we import from Asia, and that's the problem. And that's a challenge of us to find some networks that we can change in this thing about. Something about the function of activated carbon. The main function is the porosity. We speak about activated carbon when the inner surface is higher than 450 square meters by gram. Very important pore system is the distribution of this pore system, where we find different sizes. We find macropores, mesopores, micropores. I show you the size of this. These are pores in nanometer square, and one of the main is the physical adsorption of the main function. And this is it depends from the size of the vapor pressure of the molecules, pore size and form, kinetic effects, and so on. Physical adsorption is reversible and exotherm, and driven is it with van der Waals forces, with Persian forces, and dipole-dipole interactions. Another function in activated carbon is a chemical reaction. It calls chemisorption. It's driven by chemical bonds, electron overlaps, acid, base, redox, or complex reaction. In general, is it reversible, and we need a special kind of carbon. We need an impregnation, a react partner for the molecules, and this react partner can impregnate it, or it can doped in the carbon matrix. We find in the market different kinds of activated carbon. The main carbons, especially for gas cleaning, are pelletized carbon with different diameters. The main are 4 millimeters for gas cleaning or air cleaning. We find 2 millimeters in car applications, for instance. The most is there is a mixing process and there is a pressing process for the pelletizing. Other things, we find granulates. Granulates in the most time are direct activated from the raw material. There's no using of a binder. Special kind of carbon are ball coals. These are not so much producers of this, but we have here in the water cleaning, in the liquid cleaning, we find a lot of powder of activated carbon. Here are some main applications. One application is the purification of tape water. We have here something about the wastewater treatment. Other things are exhausting of air cleanings. There's special the removal of VOCs, H2S. H2S is our topic from AdFiS. Odors, mercury, and so on. We have a lot industrial applications. Industrial applications for gas purification. Food industry is a big market. We find some special carbon in medical and safety applications, and the car industry. The car industry is in the reduction of the emission of the fill of tanks, of tank systems, but in the future it will decrease this market. But cabin filter is a big thing, is a big market for a big application for activated carbon. Here's some typical processes how we generate the pore system. The main is the physical activation, and this is mainly in 2 steps. First, we have a carbonization process. This carbonization process for the material goes with temperature between 400 and 800 degrees. It depends on the material and so on. And the second, the main step is the gas activation. The most work with water steam, others work with CO2 or O2. We find some reactions here. With this physical activation, we formed open pores, like here in the picture. The other kind to make the pore system is a chemical activation. There we mixed the unshared material with a dehydration agent, and the most with phosphoric acid. And then we have a temperature process after this. With this process, we formed it called bottleneck pores. These bottleneck pores are very special in the kinetic, and they have a big volume for the absorption, and the desorption is a special kind. The chemical activated carbon used in the most for the car applications with petrol gases to reduce the emission. Yes, this was something about the basics, some pictures. I must say thank you and hope today and in the future that we can have some connections to develop the activated carbon, that we can network together to bring back the research, the science, and the knowledge to the Baltic area. Thank you.
Thank you, Thomas. So good to hear this. And I must say, from step to step, I have a better understanding of the activated carbon processes and so on. It's so important for us who are not that much into this field to really understand what we are talking about when we try to find solution providers for your challenge. So it's really great to hear this, and it's interesting that the Baltic Sea seems to be the cradle of this activated carbon thing. So great to hear this. I would take, if you have questions in the audience, so I would take the question to the Q&A part after all the talks. I hope that's fine with you. You can, of course, already put your questions in the chat if you want. Okay, so we now come to the next speaker, and it's Corbinian Ketzel, and I need again to read this from my notes. Corbian conducts research at the Department of Grassland Science and Renewable Resources and at the Competence Center for Climate Protection and Adaptation at the University of Kassel. And I checked a bit in the web about you and your expertise, and I saw that you said of yourself, this trying things out, wanting to discover something new, that's the element that runs through my life, the explorer, so to speak. That's what you have. That's what I found in the web, and I think that fits perfectly with our, let's say, hackathon spirit. And I'm really looking forward to your talk. And the floor is yours, Corbinian.
Thank you very much, Gudrun, for the introduction and also for the invitation to present a little bit about our work. And I guess it fills a little bit the gap between the talk of Thomas and of both Thomas. So also we were looking on alternative materials for activated carbon production, and on this we focus on residual biomass. And mainly to summarize what Thomas Stift mentioned already, the main problem we see for activated carbon is that it's based on that fossil resources are mainly used. Fossil coal is used as a feedstock, of course also coconut shells, but mainly hard coal or fossil coal. And within these activated carbon production, we have a high load or high CO2 emissions to develop these pore structure. So, and as Thomas already mentioned, there are typically two options to generate these pore structure either by a physical activation with water steam or a chemical like with with phosphoric acid. And just to give you a figure, so it's really on the higher side, but we have CO2 emissions of up to 18 tons of CO2 equivalents per ton of activated carbon produced. So it depends on the feedstock. 18 tons are really on the higher side. If we are using fossil-based coal for coconut shells, it's a little bit lower, but these are the emissions we are facing. And to overcome this problem of high CO2 emissions, we have to find new feedstocks for AC production, and of course also sustainable feedstocks, because coconut shells is also not the future of activated carbon. And typical applications for me are, of course, wastewater treatment, as Thomas Windgens already mentioned, for the removal of trace elements or organic micropollutants, but also in biogas cleaning, in the desulfurization, where AdFiS is located, is a high demand of activated carbon. So, and on the other side, we face a severe underutilization of residual biomass. So we have a lot of residual biomass available also in Germany, for instance, extensive grassland from nature conservation areas. So we have more than 4 million tons of dry matter available, which is not used at all, of grassland biomass. The advantage is there is no competition of use. And of course, we have to maintain also these nature conservation areas to preserve the ecosystem services. The problem, and this is why it is a residual biomass, is that it has a very heterogeneous composition, a high ash content, high mineral content, and thus it is only partly suitable for a direct thermochemical conversion and activated carbon production, which means we need some pre-treatment to improve the feedstock quality. And in this presentation, I would basically talk about this figure here. So this is also what we investigated. So we had some experimental boundaries utilizing landscape conservation biomass. In the next slides, I will show you some results where we used orchard meadow and wet meadow in the project, which had a very high ash content of 20% for the orchard meadow and roughly 6% for the wet meadow, still quite high. So we harvested these nature conservation biomass. We pre-processed this biomass in the so-called IFBB processing. It's mainly a mild hydrothermal treatment where the biomass is mixed with warm water for a certain time and then mechanically dewatered. And this transfers roughly 50% of the minerals into a press liquid, which could be used for anaerobic digestion. And the ash-reduced press cake, where we had roughly 10% in the orchard meadow and roughly 3% in the wet meadow, can be then used for activated carbon production and for wastewater treatment. The final step for the AC is, in this case, in this scenario, the incineration with the excess sludge from the wastewater treatment, where also the adsorbed organic micropollutants are removed. And the yellow line is the system boundary for the greenhouse gas calculation of the process. So what have we done in this research? So basically, we used the press cake from the biomass processing, what you can see here in this picture, and we did a one-step activation. So not, as Thomas mentioned, first a carbonization and then an activation. So we combined these two steps in one step in a small auger reactor. So the scheme you can see here, which means we fed the biomass pellets into the reactor, which was heated up to 900 degrees. And then the biomass was transported by a screw through the reactor in connection with steam, which we injected also in the reactor. So the residence time of these biomass/AC pellets was roughly 25 minutes. And we calculated the oxygen in terms of steam we applied based on the carbon concentration in the biomass. So we calculated how much steam we have to add to oxidize, in theory, 0% of the carbon, so without oxygen, 50% of the carbon in the biomass, and 100% of the carbon in the biomass, using the assumption that the carbon and the steam, the oxygen in the steam reacts to carbon monoxide and hydrogen. And the aim was to produce some activated carbon, which you can see here on the right side, for organic micropollutant in wastewater treatment. And we compared the performance, or we compared it with 2 commercial activated carbon. This is a picture from our laboratory reactor system. So we also characterized the activated carbons, and that's what you can see here. In gray and dark gray, the 2 commercial activated carbons. This is the surface area in bars, and the iodine number, which is also a measurement for the surface area, in the black squares. And yeah, we see that obviously the surface area of the conventional is more than 1,000 square meter per gram, so it's really high. The wet meadow, we had roughly half of it, and the orchard meadow was even less than the wet meadow. The hatched area is the mesoporic surface area, and here you can see that we are getting quite close to, with the wet meadow to the conventional activated carbon. So we almost reached the same mesoporic surface area. And this is the same also for the pore volume, what you see on the right side. Again, gray the conventional, and blue the wet meadow, and brown the orchard meadow. Total pore volume and the mesoporic volume. And also there, we had roughly half of the total pore volume with the biogenic ones, but we are getting close to the mesoporic volume, which was quite promising. Nevertheless, we are far away from the typical characterization of conventional activated carbons. Nevertheless, we analyzed the adsorption performance of 15 organic micropollutants. So we grouped them together. So we had, I will not go through all of them. So these are mentioned in the Micropollutant Competence Center of Baden-Württemberg. So we investigated in total 15 organic micropollutants, which are typically found in wastewater. And in this plot, you see the summarized version. On the y-axis, the reduction of all of these OMPs, and on the x-axis, the investigated concentration of the activated carbon. Again, in dark gray, one of the conventional activated carbons, and light gray, the other activated carbon. Blue, the wet meadow, and in orange, the orchard meadow. And the interesting outcome for us was that with the wet meadow in blue, we almost reached the same reduction as one of these conventional hard coal-based activated carbon. So what you can see here in these lines, that the wet meadow at a high oxidation had almost the same OMP reduction than the reference activated carbon. So what we did then was to calculate how much of activated carbon from the biogenic ones and the conventional do we really need to achieve a 50% reduction. So we selected 50% as a threshold from all of the activated carbons. And this is what you see in this figure here. The red line marks the gray one, the Norit SRE Super, as a reference activated carbon. The black one is another one. And I have to admit, if we are focusing only on this bar here on the OMP group 3, which corresponds to this figure here, that the other conventional activated carbon performs really incredible good. But the activated carbon produced from the wet meadow here on the right side, the blue bar, achieved almost this. We need the same amount of activated carbon than of the Norrid SAE Super. But you also see that with increasing oxidation, the demand of the biogenic activated carbon was decreasing. So higher oxidation, higher surface area, higher mesopore area, mesopore volume, the demand is decreasing. And we see also a significant difference between the orchard meadow and the wet meadow. From the orchard meadow, we need roughly 2 times the amount of activated carbon, and also 2 times the amount compared to the wet meadow. So we used this data, in particular data from this plot here, to calculate a greenhouse gas balance by calculating or by using as a functional unit the required quantity of activated carbon to reduce 50% of the organic micropollutants and 1,000 cubic meter of wastewater. And we used a so-called gate-to-grave approach. So we were assuming that the biomass, so we were not considering the harvesting and of the biomass and transportation. We were only using data from a gate, from a pilot plant, or from a plant where the activated carbon is produced. And then we used coarse data from the production, biomass processing, utilization, and finally the incineration. And the result of the greenhouse gas balance is what you see here. On the left side in green, we have savings from the biomass processing, from using the liquid phase for anaerobic digestion, recovery of heat from the pyrolysis, and so on. And on the right side, you see the associated emissions. And the final result is, from the wet meadow, we had in total 3 tons of CO2 emissions per 1,000 cubic meter of wastewater. And from the best performing conventional activated carbon, we have 30 tons, so 10 times the amount of CO2 emissions, considering that we need more from the biogenic one than the conventional ones. And the difference between the two conventional is simply because also there we need different quantities of activated carbon. And even the more or less poor performing orchard meadow activated carbon had a 3 times lower CO2 emissions than the best performing conventional activated carbon. And with having a look on the time, I will also come to an end. I will only give you an overview. We further improved the process by investigating the effect of the residence time in the pyrolysis and activation reactor, and the amount of steam we were adding in terms of surface area, which is the solid area, solid dots here, and in terms of pore volume development. And what we see is that with an increasing residence time, the surface area is increasing as well. The oxidation, the steam, we increase the surface area until it accumulates, and we have again a decrease of the surface area, while the pore development and pore volume development is a little bit later. So probably you can see it here. When we reach the highest surface area, we haven't reached the highest pore volume. So we further improve this process to have more reliable results. This was an experiment with hedge trimming, also with a high ash content, and we also improved the biomass processing. So what we successfully could demonstrate is that biogenic activated carbon is in general, also from grassland, is suitable for OMP removal. The problem is that the current characterization parameters are only partly suitable for predicting this, the performance. And within the pyrolysis and activation, we have a high burn-off rate. So roughly 90% of the mass is lost. It's evaporated in terms of syngas losses. And this results also in a loss of stability. So this is the result of an activated carbon produced from pellets, so from really dense pellets. So this one-step activation is only suitable to produce powdered activated carbon. And the challenges we see is that we have to that we need a constant quality of the activated carbon. So we have to improve the feedstock processing to achieve this. So because it's mainly driven by the feedstock. And for the granular or shaped activated carbon, we need a further processing. We need some binder. So we have a pyrolysis, then we need some binder to compact that and an activation step. And there is our research question: what is a sustainable binder? Is it also possible to re-agglomerate the powdered activated carbon, to reactivate them? So there is a lot of research necessary to fill this gap. And coming to an kind of an outlook, this is what we are doing now in the next 4 years. So we are working on the specific pre-treatment of biomass, using the waste streams not only for biogas production. So we are aiming to produce platform chemicals for plastics from the liquid phase, and of course we are also looking into the hydrogen and green hydrogen production and as a byproduct of the pyrolysis and activation. And we will conduct a complete life cycle assessment to simply to evaluate the whole process, to have some answers on that. And with this, I would like to thank you very much for your attention. I would like to thank my team, what you see in these pictures. I'm open for questions. Also here on this QR code, you will get directly to our website. Please contact us in any case you have questions. So thank you very much for your attention and also the option to present in this bio booster. Thank you very much.
Thank you, Korbinian. Very interesting. Thank you so much for this interesting presentation. I think we could have included your challenges also into the AdFiS challenge. So no, just kidding. So, but it's there seems to be really a lot of challenges still in the activated carbon research. So it's very interesting, and let's see if we can also contribute a bit with our hackathon to your challenges as well. So, but I know you are already in contact with AdFiS, and so there will be anyways a connection and an exchange about what can be done. And okay, so thank you so much, and we will put the questions again at the end. I hope you can still be with us until the end. That's great. Okay, then we come to the, let's say, most crucial or most exciting part of this today webinar, and that's the introduction of the AdFiS challenge that we put into the core of the hackathon. And this will be done by Toni Miersch from AdFiS, and Toni is head of R&D at AdFiS, and he will introduce the challenge for us.
Okay, you see everything?
Yes, we do. Again,
Perfect.
just not the speaker modus, but
okay. Yeah, I forgot. Sorry. I think it should work. Yes.
sorry. Yes, I
Yes.
muted my phone.
Okay. Perfect. So thank you, Gudrun, for this kind introduction, and also for the previous speaker for your interesting talks. I want to present you our 2 challenges that we have in our company, AdFiS Products GmbH. I want to start with a short presentation of our company. Then I want to show you the state-of-the-art process. So this overlaps a little bit with the talk of Thomas and Korbinian. And then I want to present you the 2 challenges. We also have a small video. We show some minutes. The AdFiS Products is a company in the heart of Mecklenburg, Western Pomerania. You can see it at the red dot. We are in the middle of Mecklenburg, Western Pomerania. To the best to our known, we are the only producer of activated carbon in Germany. We produce from renewable raw materials. These are charcoal and a sugar-based binder named molasse. which is derived mainly from also Western Pomerania in Anklam. And we are specialized in the purification of gas streams, especially the biogas stream is of our interest. We produce about 1.8 thousand tons of activated carbon a year. Our unique product is the so-called Dopetech Sulfur 100. This is an activated carbon, the most efficient way of fine desulfurization, we always say, because you need fine desulfurization in the biogas market, because the biogas process produces a lot of H2S, and H2S is quite corrosive in the engines that produce energy and electricity after the biogas process. And to save these engines, we need to absorb the H2S from the raw gas on activated carbon. This process was developed together with the Fraunhofer in the early 2000s, and it's also patented. And yes, then I want to show you a small video which summarizes the whole presentation in a short way, and at the end I will give it to I would describe it a little bit more detail. Gudrun, it's your turn.
Yeah, thank you. So we have the presentation for a minute. We are so happy about this video, so to say, that we could realize in a very short term. Okay, now you should see.
At AdFiS Products, we produce approximately 1,800 tons of activated carbon annually, making us the market leader in Germany since 2014. Our high-performance activated carbon is essential for desulfurization, air purification, and the removal of siloxanes and ammonia, with application in biogas, sewage gas, and landfill gas treatment. The process begins with raw material preparation, in which charcoal is crushed into small particles. A binder and additives are then mixed in. Next, the mixture is pressed into pellets and dried to ensure they are ready for further processing. Once dried, the material undergoes carbonization and activation. In the carbonization kiln, volatile substances are removed, and the material is then transferred to an activation kiln, where a porous structure is developed. During gas and steam processing, steam at up to 900 degrees Celsius is generated and used for activation. The first challenge is making this manufacturing process more energy efficient by incorporating nanoparticulate organic additives that vaporize at lower temperatures. The last stage involves sieving and packaging. Undersized material is removed to ensure consistency, and the finished activated carbon is packaged and prepared for transport. During the sieving process, we find that nearly 1.5% of the activated carbon consists of undersized material. The second challenge is finding a binder that can pelletize the undersized material without closing the pore system. Currently, Europe produces only 20,000 tons of activated carbon annually, while 400,000 tons are imported from Asia. Successfully solving this challenge could not only make our production more sustainable, but also revolutionize the European activated carbon market, creating opportunities for new businesses and reducing reliance on imports. We welcome innovative ideas, research collaborations, and fresh perspectives that can drive the future of activated carbon technology. Join us. Apply before April 11th, 2025 and be part of the innovation process at the AdFiS Hackathon. Let's create a more sustainable future together.
Yeah, so that was the video. I hope you enjoy. And now, Tony, can you
Yes, it should work. So, this video was really fantastic, and it summarized the whole presentation in such a short way. I'm not sure I can tell so much more, but I will try. First up, I want to show you our state-of-the-art process again. We start with charcoal. Charcoal, we get it from the Ukraine and Poland, and also some from Germany. It's like charcoal, from a barbecue. This charcoal has a native pore system in it. It's not as big. It's more or less 300 square meters per gram, 400. Most of the pores are not open, so they are not accessible for any adsorption process. In the two-step grounding process, we mill this charcoal to charcoal powder, which is very fine. And after this, we use a binder called molasses, and we mix them. And with a roller press, or in German we say collar press, this mixture is pressed to pellets. These pellets are still very soft, like rubber. And after drying them at about 100 degrees, these get very hard and can undergo a further processing. The further processing is the so-called carbonization. During the carbonization at 450 degrees in the rotary kiln, volatile matter from the pellets are evaporated or decompose, and we get the so-called carbonizate. We still don't have a huge accessible surface in the molecules. For that, we need an activation step. It's at 900 degrees as well in a rotary kiln, and we add some steam and some air to the process. And this water steam reacts with a native pore system. It oxidizes the carbon and widens up the pores, so that we get at the end a widened pore system consisting of macropores, mesopores, and micropores. After sieving process, we get mainly 98.5% of our target product. This is packaged, storage, and sailed. And we also get 2% of undersized activated carbon, which should be addressed in the challenge number 2. First of all, challenge number 1. The general pre-process should be the same. The problem is the whole process is quite energy intensive, as Corbinian showed in this presentation. So to reduce the energy demand it's very important, and maybe one strategy is to implement or to use a nanomaterial, especially an organic nanomaterial, which should work as a template for pore generation. This is given to the mixture. Afterwards, it's pelletized and dried and carbonizated at, we don't know the correct temperature till now, maybe 450. It's important and it's less than in the actual process. And with this nanomaterial at quite low temperatures, these materials should decompose and make holes in our native pore system, and so produce the resulting pore system at much lower temperatures. I think it's quite crucial that this nanomaterial needs to decompose. So inorganic materials should not work in the theory, and it should be also in the good price range, and it should be also available in quite high amounts. Nevertheless, we also have our 2% of undersized activated carbon. So this is also also a challenge that we want to address. As Corbinian told, this is also a challenge of the whole activated carbon research in the next years. how to pelletize or how to bring already activated material back in the form that it can be used. For this purpose, we are looking for a new binder, which is possible to glue together this already activated undersized material. The problem is, I want to illustrate it on the right. This is the activated carbon particles. When we went, the most binders we use have the problem that they block the pores. So the pores are not accessible for any target substance. And so this activated carbon has no pore system anymore. The clue is to find a binder that only sticks or that not blocks the pores. Another crucial thing at this thing is that activated carbon has some kind of lotus effect. So there's nothing really that sticks on activated carbon really good. And that's the reason why even when you found something that don't block the pores, you have the problem of pellet stability. But that's why it's a challenge, and we have no solution till now for this. And with that, I'm already finished and open for question. And I thank you also for your attention.
Thank you, Tony. That explained it a bit more in detail, and I think it's a perfect fit between the video and your presentation. Thank you so much. And we would now have some minutes for questions, if there are some. I might start until there might be more. So you already mentioned it when we discussed about the challenge and so, but I'm still not sure about that. Does nanoparticles are really the only option for the first challenge? So it has to be something organical. That's what I.
Yes, it should be.
Okay.
It should be organic because I think it's better. Organic material will decompose much easier at this temperature than anything inorganic or mineralic or yes, it's not important that it should be a nano-sized material because the pores we want to generate are in the nanometer range. So the smallest pores we are interested are in the sub-nanometer range, but the most interesting is between 2 and 20 nanometers, and therefore the material, which is some kind of placeholder in the material, should be in the more or less same range.
Okay, I understand. Okay, thank you. Are there questions from the others? So feel free just to open your mic and ask your questions. Maybe it was crystal clear with the videos and the explanation might be. Okay, I can ask another question, maybe in between there's someone else. So about the Asian market, is it just a matter of cost that so much of activated carbon is imported, or is it? I mean, do they have other processes to produce it, or is it really less salary costs or something like that, as it's usual when we?
I think it's a combination of different things, but they all result in cost. Yes. I think first of all, the payment of the workers is much lower in China than in Europe, or especially in Germany. Then the resources of hard coal will also be much cheaper than in Germany, in the availability of hard coal as well. And the environmental regulations in China are also not as strict as in Germany. And so the process in our plant is for activated carbon generation quite energy efficient because we use the energy which is generated during carbonization, we use it in the activation, and the energy which is produced during activation is used in the carbonization. So this is worldwide quite unique, and it's not such a big thing in Asia till now. Yes.
Okay, thank you. So Thomas, you also want?
I will answer on top. The problem is the price and the investment for such a plant. 2 years ago, we made plans for a new plant in Germany. We want to build a new one. We make a detailed plan for this and find a lot of investment costs and nearly 40 million euro for our plans. And the same plant built in China costs $5 million. And that's a problem what we have between the 5 million to the 40 million. There are a lot of invest what is not possible. I don't know. We have the government and we have the restriction of this, and the Chinese have this not. And added to the reasons what Tony told, we are so in the prices higher than the Chinese.
Okay, thank you. So Eva, do you have a question?
Yes, I was just wondering. So the Chinese coal is not fossil coal; it's biocoal as well. Is that correct?
I would say on the worldwide market, it's most often fossil coal.
Yeah.
And that is of course also a price difference to coal from charcoal.
Yeah, quite a big difference. But we have coal producers coming from primarily softwood in our place. They aim to support the mining industry with the carbon for reduction, the iron. But I'm just thinking, you've been trying out with different kinds of charcoals. Do you see any pros or cons with charcoal from softwood or hardwood, or does that matter?
So during my time and also before, we tested a lot of different charcoals from various sources. And in former times, we thought, okay, coal from softwood, it should not work due to ash content, volatile content, and hardness. But quite new analysis shows that it should work also. It's a possible strategy to reduce costs as well for us.
Oh, okay.
And there are also rest materials from maybe palm kernel shells, which can be carbonized, and they should work as well very good. And it's biogenic. Yeah, normally it's waste where in West Africa and Indonesia.
Yeah, thank you.
Okay, Corbinian?
Yeah, I just want to say I see some other challenges, not only from the production side. So Thomas and Tony are completely right. So in Europe, it makes simply no sense to produce also from hard coal activated carbon if we are importing the raw material. During the activation, we have 50% mass loss, which is, but yeah, it's simply gone, it's lost. So it makes no sense to import the raw material to do only the activation in Europe. Makes no sense. And also the regulations are really challenging for all the activated carbon producers. But another challenge I see is as a producer, you have to ensure a constant quality. Otherwise, you will simply nobody will buy your activated carbon. And if we are using different types of raw materials, if it is not only softwood, palm kernels or something like this, we have a heterogeneous input material to a certain extent, and this must be somehow compensated. So I guess there are some options, but my experience is that consumers, they simply have the feeling, or they want to have always the same quality. And this is not only for activated carbon, we have this in the whole industry, in the whole purpose. So if I buy some clothes, I'm expecting to having always the same color. And by using alternative input materials, this is probably not possible. So I guess this is something we have to deal with in the future. So if we are really want to get CO2 neutral in the future.
Yeah, thank you for this explanation. Very interesting and very challenging. It sounds like that. So yeah, okay. Is there another question? I can't see any in the chat. You are, of course, always invited to put your questions still in the chat, but then I would close the open discussion here and would like to come to the last but not least interesting part. It's from Anna Alto. Anna is the lead partner of our BioBoosters project, and yeah, she guides us excellently through all the aspects and everything that we have to consider when doing such hackathons, and she will give you that are not that much involved, especially a kind of idea what is BioBoosters, the BioBoosters frame. So Anna, the floor is yours.
Thank you. I trust you can see my screen now.
Yes, we can.
Yes. So I'm happy to be here to introduce BioBoosters, and that includes the hackathon model and the network. And apart from those, we are also operating in BioBoosters, a business accelerator here in YAMK, University of Applied Sciences Institute of Bioeconomy. So a lot of different BioBoosters, but I hope you can follow the discussion in the coming slides. So here we are, the BioBoosters network, and all of us are now taking the task to find solutions for this challenge presented today. This network of networks will be of assistance to find suitable specialist mentors and also to find these solution provider teams to this challenge presented. And we will take this launch webinar messages and the recording with us and use that as our guide to find suitable solution providers. And as you can see, we are from all around the Baltic Sea region. There is 9 organizations. All of us are innovation hubs in our regional innovation system. And our regional innovation systems are focused in certain bioeconomy sectors. And we have this aim to boost the circular transition of these bioeconomy sectors. So from Sweden, our partners are Biofuel Region and Paper Province, mostly focused on the forest-based bioeconomy sectors. Viteno is, of course, hosting us today from Germany. From Poland, we are represented by ProCivis Foundation as a regional developer of bioeconomy from Świętokrzyskie region especially, but also having national and international development activities in the field. From Lithuania, we work with Sunrise Tech Park, a national cleantech cluster organization, and also a very prominent startup accelerator, and having international recognition just recently. In Latvia, our partner is Vitseme Planning Region, that is a national leader of bioeconomy and food cluster. and a very active developer in the bioeconomy field. And from Estonia, we work with the Estonian University of Life Sciences and Pärnu County Development Center. I myself, as mentioned, I'm from JAMK University of Applied Sciences from central Finland. We are stationed in Jyväskylä and also in Saarijärvi at our rural bioeconomy campus with the smart farming, testing environment and demonstration facilities. I hear we are going to have very soon there also biochar and active carbon production in a pilot scale, and that was very exciting news for me. And we hope to connect the experts from this development project to also this hackathon. But we will talk more about that later. So BioBoosters, the network was presented. Now we come to BioBoosters, the project. And the project is funded by the Interreg BSR program. And we have this 3-year funding to implement 18 business-driven hackathons and hoping to launch up to 20 research, development and innovation or business cooperations to solve these challenges. And the hackathons, they bring together a lot of specialists from business, research and different fields. So together with these 500 hackathon participants, we are leading the circular transition of bioeconomy sectors in the Baltic Sea region, tackling these 18 specific challenges. And the AdFiS challenge presented today is the final of these 18 challenges. So it's a bit sad feeling as well to see the last one go out, but we are proud of all of the hackathons before and also very much looking forward to these last ones coming this spring. And I will give a little bit more details on these hackathons in this presentation. And the framework we are working on, the circular transition of bioeconomy sectors, we are focusing especially on sustainable biomass sourcing and optimizing the use of the biomass throughout the value chains, and especially also valorizing different side streams and returning the nutrients and CO2 to the natural nutrient cycle. The hackathon, the BioBoosters hackathon, is a very well tested process. It's an open innovation platform that is focusing on solving a specific challenge from a company or companies. So we want to have there the challenge provider who is willing and interested and able to start a cooperation with the winning solution provider. And that is the baseline for this whole process. We have previously tested this for a few years in a national scope with the lead of JAMK, University of Applied Sciences. We have done about 15 hackathons before starting this international piloting, and at the moment I think we are all combined with more than 30 hackathons. So all these hackathons have delivered us a lot of experience on this process, and we are all the time applying all the lessons learned to make this work as well as possible to solve the challenge and to launch the cooperation in the end. So now we are already taken a few steps from this process. We are here at the launch. We are launching the open call, and this is where we start to attract the teams to this process. We are using active scouting via the networks. We have direct contacting and also different communication channels and means that our network has to find solution providers to apply to this open call and to come up with their solution ideas to solve this challenge presented by AdFiS. And the call closes on 11th of April, and then we are ready to select the teams. So AdFiS team will select based on who they see the most potential to start a cooperation with, and then these selected teams will enter the hackathon process. We are signing non-disclosure agreements, and we are bringing these teams and mentors and the challenge provider together for the first time at a kickoff event. Is it the 28th of April, if I'm not mistaken?
I think so. I need to check my slide. But yeah, it is.
Yeah. Okay, so that's where the interaction between the teams, mentors, and the challenge provider starts. The teams are able to share their ideas, and the mentors and the challenge provider are able to give feedback and guidance on how to develop that idea and cooperation proposal further. The co-working will continue on a digital platform at HouseSpace. And then we come to the hackathon days on the 20th and 21st of May. And here we mainly face-to-face with a hybrid possibility if some participants need to participate online. We will carry out more in-depth mentoring for the teams. Networking opportunities will be available, and then at the end of the hackathon days, we will have the pitching competition with the jury led by AdFiS selecting the winning proposal, and that is the starting point for cooperation with AdFiS to solve this presented challenge. And these are the companies we have worked with so far before the spring, and the challenges we have solved so far. So the AdFiS challenge is a good addition to this mix. And we are happy to say that all of these 13 challenges so far have had a very good outcome. We have identified solutions, and corporations have started in many cases in practice. So the overall numbers to this day are 17 launched corporations, 10 of them international, 170 applicants to these 13 challenges, and 90 teams selected to join the hackathons. And by the end of the week, the numbers will look different. We have a new hackathon finished by the end of the week, and then we will have even more to share. But we have a very good range of nationalities represented in the teams as well. The countries from Baltic Sea region, but also other EU countries and beyond EU have found their way to the hackathon, and the international level has grown as the piloting has proceeded. We are also growing a community in LinkedIn, and already we have more than 400 hackathon participants that have recommended their experience and are happy to promote us further. During the spring, we also have 4 other hackathons going on. So as mentioned, this week we are closing the Nordic Hemp Hackathon in Estonia. And at the moment, we also have a call open for Piesta Hackathon and Reval Hackathon related to side streams of apple production and valorization of those. And then we have in Lithuania a challenge open for soil remediation solutions. And all our active calls and results you can find in our LinkedIn page. So that's a good site to follow for the results of the spring hackathons and later outcomes of the started cooperations. We also have a publication on the first 9 hackathons available if you are interested to check out what can happen at the hackathon and what can be the impact. So thank you for this time, and sorry if I'm a bit over time. So happy to answer any questions if you would like to contact me later, or I can also stay for a while if there's something in the chat.
Thank you so much, Anna. Always nice to see this, also the results. So really amazing what could be achieved already. So I will share 1 second again my screen, but then we are more or less finished. So you already mentioned this, Anna, that our timeline, I mean. So just to make it visible for you as well. We had the launch webinar today. So I have a block here in my screen. No, the call closes. I mean, all the applications should be submitted until the 11th of April, kickoff 28th of April, and then the hackathon days in May. That's the timeline. We are looking forward to this. It's always, also last year was Kusun Beat. It was really an amazing process, and we are really happy to be part of. All those who couldn't be with us today will be able to get the recording of this webinar today. Also, this nice animated film will be visible. We will put it to the BioBoosters LinkedIn channel, as it explains the best way what AdFiS is looking for. A corresponding post will follow very soon. Yeah, and then we are looking forward to many exciting and interesting submissions. All are welcome, very well welcome, and I thank you already, all of our partners, that they will help to find interesting solutions. I thank you all for your contribution today, for your interest, for your questions, and yeah, wish you all a nice afternoon still, and hope to see you all very soon again. Thank you so much.